Yeah, hello everyone, and thanks for joining. So today I'll be talking about how machine learning is used in high energy physics to model multiple detector geometries responses, and more specifically, the calorimeter subdetector, and this is in a high energy physics context. So when we talk about detector simulation, we have to talk about Giant4, which is a toolkit that provides a highly flexible simulation framework in C++. And Giant4 is actually the cornerstone for simulation of Large Hadron Collider experiments at CERN. So here I put an illustration of how Giant4 actually does the particle interaction simulation. So let's suppose we have a usual high energy physics setups. So we have the subdetectors around the beamline where the collisions happen. So the innermost subdetector is the tracker to measure the trajectory of the particle. And then we have the calorimeter to measure the energy. Of course, there is some structure in the subdetectors, and this represents the detector readouts. So we have a particle which enters the detector, and there are a lot of physics processes happening in the passage of this particle. And then at the calorimeter, or in the calorimeter, so particles will lose their energy in a cascade of secondary particles, and this is what we call a shower. So the blue and the red shapes are actually the energy deposition of this particle that creates the shower. And this is actually what we reconstruct and analyze. So this simulation is called full or detailed because it really models the step-by-step interactions. And you can imagine that this is a slow process. So this is why there is a need for fast simulation approaches in order to speed up the simulation to generate more data within the same CPU time. So if we look at Large Hadron Collider experiments, so if we take the example of Atlas, so here we have the annual CPU consumption as function of the years. So if we take and if we rely only on the full simulation, so this is the baseline, so you can see that it exceeds our resources. And this is why we need a fast simulation approach. And this is the same for the other LHC experiments. Another application of fast simulation approaches, and this concerns more future experiments where we don't have a detector built, but we want to do physics studies and detector performance. So here you can see with the fast simulation approach how we can decide on the calorimeter resolution by looking at the physics observable, which is the Higgs mass peak. So instead of full simulating the cascade of particles, so a fast simulation approach would parameterize the energy deposition in a single step. And to answer the question how to do this, so in our project we are using a machine learning approach. And what we want to have is this beautiful function that learns to generate showers using information of the detector geometry or the calorimeter, but also information of the incoming particle or the particle that generates these showers. And what I mean by that is the type of the particle, the energy, and also the angle, which means the direction at which the particle enters the detector. In our project, we want not to have a model that works for a single detector geometry, but rather a generalizable and reusable solution. And for that, we have to train on multiple detector geometries, and we need a fast way of also adapting when we have a new geometry coming. So technically, what we have is two environments. So the Giant4 one, which is a C++ environment, and then we have the machine learning one, which is, of course, a Python-based environment. And the two environments are connected through converters. So the first thing to do is to have the full simulation. This is what we train on. And then in the machine learning pipeline, we have all the steps of preprocessing, definition of the model, training, tuning, optimization, and the validation in our case is to compare the full simulation and what the machine learning model has generated in terms of physics observable. So these are the quantities that we care about. So let's say once we are happy with our model, we save it into a format that can be used for inference in C++. And then once we have that, we can generate our fast simulation samples within Giant 4. And of course, the inference also can run on different hardwares. So I mentioned that the generalizable and reusable solution is trained on different calorimeter geometries. And if you look at the geometries that I put here, so you can imagine them as a cylinder, and they are segmented into R, so the rings, into phi, so the angles, and also let's say the depth of the calorimeter, which is here the number of layers in the z direction. And the differences between the different geometries is in terms of the material used in the geometry, let's say the number of layers or the thickness of these layers. And throughout these slides, I will be referring to these different geometries as SIW, CPB, or PBW04. Yeah, and also the number of readouts cells, that we call them cells, or you can imagine just segments in this RF and Z directions. So we have 18 by 50 by 45, which is pretty a highly granular definition of showers. So here you can see in a 2D plane, so the XY or the R phi, how a shower would look like. So the different colors here represent the intensity, or let's say how much we have energy deposition. So if we, for example, look at the energy as function of the different rings, so this refers to us as a transverse profile. But in the other case, if we look at the energy as function of the z direction, so this is the longitudinal profile, and this is how a shower would look like in the x and z directions. So in order to have this fast simulation approach, and which is trained on multiple detector geometries, so we are using a meta-learning approach, which is the process to learn fast. So, and you can see a meta-learning approach as two steps. So the first one is the meta-training, where we would like to have a prior knowledge, or let's say the meta parameters theta zeros, and these are the weights that we want to learn. And then the second, and then the second step, we would use these meta parameters as an initialization of the model in order to get the specific parameters for our specific geometry, or let's say a task that we know in machine learning, we call them tasks. So we start from theta 0, and then we optimize to the specific geometry or the specific task. And if we look in the literature, so there are a lot of papers on meta-learning. So we can find the most, let's say, two well-knowns are the model-agnostic meta-learning, and the second one is Reptile. So Reptile takes less time, and also it's faster because it does not enroll computation graph, or it doesn't compute the second derivative. And it works by running a stochastic gradient descent on a specific task, and then updating the initialization weights. So this is the algorithm. So, and then updating the initialization weight towards the weights that you can get after running k steps of the SGD. And coming back to the two steps of the meta-learning, so I said that there is the meta-training step, and then there is the adaptation step. And for this case, I would be using the two detector geometries for the first step, and the third one for the adaptation step, to see how well our model is able to do well, or have, let's say, a a machine learning simulation which is close to our full simulation. In other words, reproducing the distributions of our physics quantities. And the data is actually available in Zenodo if anyone is interested to use them. Yeah. And the model is actually a conditional one because we want to be able to generate new showers by having us input the geometry, the energy, and the angle. And for that, we use a quite wide range of energies and incident angles. So this is for the incoming particles that create the shower. And you can guess that what we want to have is a generative model. So we are using a variational autoencoder, which is two networks. So we have the encoder, which learns a mapping of the shower into a lower dimensional space. And then we have the decoder, which reconstructs back the input shower using this latent representation. And here you can see the results of the adaptation step, because this is more interesting to see after we do the meta training. So in blue, you can see I don't know if it's clear, but this is the full simulation, which means our giant for initial data set. And in orange, it's what the machine learning model has generated. And here is the longitudinal profile, so through the z-axis that I mentioned earlier. And here you can see as function of the number of adaptation steps that the model is. So here it's 10 steps. The model cannot reproduce the distribution, but you can see with the steps, we have better and better agreement. And with 360, we have a very good agreement to the full simulation. And this is a way of validating how well our generative models are doing. So here I wanted to show you the difference between the adaptation versus a traditional training. And here what I mean by traditional training is starting from scratch on this specific geometry without any initialization. So maybe it's better to see the ratio plot. So the red one is the adaptation where we have 400 steps, and you can see that we have a very good agreement to the full simulation, and we use the same number of steps or epochs for the traditional training, also 400, so the green one, and you can see that with this number of steps, the model did not convert yet to the best performing result. So, and this, for the traditional training, we would need at least 4K steps to have a decent agreement. And also to give you an idea on the time, because I said this is fast, so 400 steps of adaptation would take 20 seconds versus 400 steps of training, which would take 1,200 seconds. Yeah, so at the beginning I mentioned that ideally we would have also a condition on the particle type. What I showed previously is only a single particle type, and this is like pushing more our model to be also able to be conditioned on the particle type and generate showers by specifying the particle type. Here you can see the longitudinal profile as well for two different particle types, so the gamma and the electrons, and you can see that we are getting also a very good agreement. And this one is the transverse profile, where we look at the energy as function of the different rings, also for the two different particle types. So this brings me to my conclusion. So the fast simulation techniques are needed to cope with the new challenges for the detector simulation, and more specifically for the calorimeter subdetector, because this is the task that takes most of our CPU, and machine learning approaches are largely investigated in high energy physics for fast calorimeter simulation. So there are models which are experiment specifics, and what I showed here is more a generalizable simulation tool that uses the meta-learning approach. There is an ongoing work to validate this on realistic geometries, and this is more for the future detectors. So we do have very promising results, and some models are already in production, which is what we want to have before at least 2023, with all the new challenges that the high luminosity LHC will bring. So I'll leave you with the Calo challenge. So this is the first ever Calorimeter simulation challenge, where we recently made it public, and it has 3 different levels of difficulties, or 3 data sets. So we have medium, easy, medium, and then hard. And I invite you all to participate and take part, and the results would be announced in the next workshop of the machine learning for jets end of this year. Yeah, that's all from my side. Thanks a lot for your attention. Okay.
Thanks for this great presentation. Do we have a few questions from the audience?
Thanks for a great talk. I have a lot of questions. I'll try to only ask 2. First, your meta-learning results are very, it really makes me want to use meta-learning a lot more in a lab's research. And then I was wondering, how did you choose the latent space size, the bottleneck size? How did you come up with 10 dimension? Was that hyperparameter tuning or something else?
Yes.
Okay.
So it was hyperparameter tuning, and for that we were using this automatic machine learning approaches, the AutoML.
Okay.
Yeah. It's pure hyperparameter tuning.
Yes, that's really nice. And then once you had those 10 dimensions, it's very attractive, because if you have only 10, you could use it for interpretability. Is it a situation where you understand how Calorimeter works so well that you don't have much to learn, or could you use that reduced dimensionality space to better understand the different regimes of showering, or the relationship between showering and the different inputs you have?
So for example, we use the latent space studies to see if we have, let's say, groups of showers that maybe cluster in some, let's say, space of the latent space. But rather than that, so we are mostly interested in really getting the generation. So after the training, we would only use the decoder as a generator, and also at the inference time, we would use only the decoder. So studies on the latent space, we did not do much on that, because this is not, the let's say the first thing that we are interested in. But yeah, that was let's say at some point done, and yeah.
Thanks.
Another quick question, maybe?
I think everyone is tired.
Yeah. Otherwise, there is the... yeah.
There's a poster outside about how graph convolutional networks are being used to encode inputs from the trigger at CERN. Do you foresee this being used in the same manner, or is this purely for simulation?
This is purely simulation, yeah.
Okay, thank you.
You're welcome.
Let's thank our speaker
Thank you.
once again.